2003 higher level question 9, the electron. So in the first part of the question, I'm going to mark 1, 2, 3, 4, and 5, 6, and 7. So that at least we know each part of the question that we're referring to. So in 9 part 1 it says list 2 properties of the electron. So of course we can say the electron has a negative charge. We could say that it orbits the nucleus. We could say because it has a charge, it is deflected by a magnetic and an electric field. So by Fleming's left-hand rule. And we could go to our tables and we could even write down its mass. But we're only asked for 2 properties here. So therefore we were getting 3 marks and there was 2 properties. So it was 3 marks times 2. So in other words, 6 marks in total for part 1 there. Part 2 says name the Irishman who gave the electron its name in the 19th century. And of course it is G.J. Stoney. Not to be confused with J.J. Thomson who discovered it. So it was G.J. Stoney who named it. So again, 6 marks for that. Part 3 then says give an expression. So in other words, write down the formula for the force acting on a charge Q moving at a velocity V at right angles to a magnetic flux density of B. So all we have to do here is go to our maths tables and identify the correct formula. So if we look down here on the bottom left, on page 62, we can see F is equal to QVB. So in other words, force on a charged particle in a magnetic field. So we'd say F is equal to QVB. And there were 6 marks going for that. So F is our force, Q is our charge on the particle, V is the speed of the particle, in other words the velocity of the particle, and B is the flux density. So part 4. Well, part 4 says an electron is emitted from the cathode and accelerated through a potential difference of 4,000 volts in a cathode ray tube, as shown in the diagram. How much energy does the electron gain? So as it moves across the evacuated tube, being accelerated because of that attraction from the high voltage across the anode and the cathode, then we have the loss in electrical potential energy must equal the gain in kinetic energy. So therefore the electrical potential energy is given by the charge on the electron times the potential difference. So if we go to page 46 in our tables, we can see the charge on the electron is 1.6 by 10 to the power of minus 19. And our voltage, we can see, is 4,000. So we have V is equal to 4 kilovolts. So therefore that's equal to 4,000 volts. The charge in the electron is 1.6 by 10 to the minus 19. And of course that was actually given to you at the bottom of the question anyway, but sometimes they don't put that into the question, which means you have to refer to your tables. So therefore the potential energy is the charge in the electron, so 1.6 by 10 to the minus 19 times 4,000, which gives us our potential energy of 6.4 by 10 to the minus 16, and that's joules. And of course, that is also then equal to the kinetic energy gained. So the potential energy lost equals our kinetic energy gained. And there was 6 marks going for that. And you could have, of course, kept it in electron volts, which would be 4 kiloelectron volts. So it then says, well, what is the speed of the electron at the anode? So as it has been accelerated from our cathode here, if we look at the diagram, and it's accelerated across to the anode, well, what speed does it have? So, of course, because we've just worked out our kinetic energy, we know that our kinetic energy is equal to a half mv squared for any moving object. And therefore, we have the mass on the electron, which if we look at page 46, our mass on our electron is 9.1 by 10 to the minus 31. Or again, if you look at the bottom of the question, it was given to us. So if it's not given to you, you refer to page 46. So we have the kinetic energy is equal to 6.4 by 10 to the minus 16 joules. And therefore, that's equal to a half mv squared, where m, the mass on our electron, is 9.1 by 10 to the power of minus 31 kilos. So therefore, we have a half times 9.1 by 10 to the power of minus 31 times v squared equals 6.4 by 10 to the minus 16. So if I multiply across by 2 and divide across by the mass of the electron, we get 2 times 6.4 by 10 to the power of minus 16 divided by 9.1 by 10 to the power of minus 31. And of course, that's equal to v squared. So if I want v, I will then get the square root of both sides. And that gives me a velocity of 3.75 by 10 to the power of 7 meters per second. So we had 6 marks for the first part, which we've written down there, so our gain in energy. Then we had 12 marks for the second part here. So we have 3 for writing down our kinetic energy is equal to a half mv squared. And then we had 6 for our substitution into our formula. So 3 for each side. And then we had 3 for getting our worked out solution. Okay, so let's go back to the question then. So we're told after leaving the anode, the electron then travels at a constant speed and enters a magnetic field at right angles, where it is then deflected. The flux density of the magnetic field is 5 by 10 to the power of minus 2 Tesla, and we have to calculate the force acting on the electron in the first part of the question, and then the radius of the circular path followed by the electron in the magnetic field. So, of course, we know by Fleming's left-hand rule that it's going to experience a force when the magnetic field is at right angles to the direction of the electron. So to find the force acting on the electron, well, in part 3 there we had already written down that F was equal to QVB. So that means our charge is referring to the electron, the velocity we have just found, and the magnetic flux density we have just been given. So in other words, the charge on the electron is 1.6 by 10 to the minus 19 coulombs. Our velocity we've just found to be 3.75 by 10 to the power of 7. And our flux density, we're told, was 5 by 10 to the power of minus 2 Tesla. So subbing into our equation, we end up with the charge on the electron, so 1.6 by 10 to the power of minus 19, by the speed, which is 3.75 by 10 to the power of 7, by the flux density, which is 5 by 10 to the power of minus 2. So that gives us a force of, so 3 by 10 to the power of minus 13, and of course it's force, so therefore our unit is newtons. So again, in any of these calculations, if we're missing our units, we will be deducted 1 mark. So again, we had 3 for our formula, 3 for subbing into our formula, and 3 for our answer. So the next part then is, what is the radius of that circular path? So we know from centripetal acceleration, and I'm going to refer to that as, I'll just call that A. and B. So we know our centripetal force is given by mv squared over r. So therefore we can work out our radius based on this path. So therefore the force on the electron due to the magnetic field is equal to the centripetal force. So by equating those, essentially what we have is mv squared over r must be equal to EVB, which we have just found. And therefore, if I want the radius is going to be mv squared divided by EVB. So we know, so that gives us 3 by 10 to the power of minus 13, and force being newtons. So we had 3 for the formula, 3 for substitution, and 3 for the answer. So the next part of the question then says, find the radius of the circular path followed by the electron in the magnetic field. So what we need to say here is that the force on the electron due to the magnetic field is equal to the centripetal force on the electron. So therefore we know that the force due to the magnetic field is what we've just found. It's our EVB. And that will be equal to the centripetal force, which is mv squared, over r. So therefore we can sub in our values. So our mass on our electron, if we look, is at the bottom of the question there, 9.1 by 10 to the minus 31, or else on page 46. We've just worked out the velocity. So we said our velocity was 3.75 by 10 to the power 7. And then we know what our EVB is. So if I rearrange that equation, we end up with V squared is equal to, not V squared, sorry. We want R. So R is equal to mv squared divided by EVB. So the mass is 9.1 by 10 to the power of minus 31 times the velocity squared, so 3.75 by 10 to the power of 7 squared, divided by EVB. So our EVB was our force on the electron in the magnetic field, so 3 by 10 to the power of minus 13. And therefore the radius is equal to 4.27 by 10 to the power of minus 3 meters. So again, we have 3 for our formula. And 3 for our answer. So the last part of the question says, well, what happens to the energy of the electron when it hits the screen of the cathode ray tube? So basically what we have is the kinetic energy of the electron is converted into light energy. Because we see the screen fluorescing. And there was 5 marks going for that. So a nice question on the cathode ray tube there. So if we do some practice questions on these in our books would be page 333, question 1, question 3, changing from electron volts back and forth into joules would be 4, part 1 and part 4, 5, part 1 and part 5. Question 6, identifying the particles. 8, 9, and again 10, identifying the particles. And then question 11 is a nice one, so looking at the charge to mass ratio. So J.J. Thomson's experiment there.